Hey, good afternoon to everyone. My name is Usha Rani. I am assistant professor in physics. Today we are discussing about nanotechnology, fourth unit. Here I am sharing my screen. Is it visible to everyone, ma?
Yes, ma'am.
Okay. Fourth unit is nanotechnology. Okay. Generally, nano means what, ma? Okay, in this nanotechnology, what are the subtopics are introduction and properties of nanotechnology and synthesis of nanoparticles and characterization techniques and finally applications of nanotechnology. Okay, generally nano means what ma? 10 power minus 9 meters. 10 power minus 9 meters. Nanometer is 1000 millionth of a meter. To understand how small one nanometer is, let us see few comparisons. Okay, and here it is used for the nanotechnology is used for the study of materials and processes at the nanoscale in variety of disciplines like biology, material science, and polymers and chemistry. In these disciplines, we are using nanotechnology. Okay, and here we are discussing about nanoscale. Okay, already we know nano means what? 1 nanometer equal to 10 power minus 9 meters. Okay, it is a billionth part of a meter. In this, atoms are extremely small and the diameter of single atom can vary from 0.1 nanometer to 0.5 nanometers. Its value is depending on the type of element. Suppose red blood cell తీసుకున్నాం. Red blood cell is approximately its value is 7000 nanometers wide and carbon atom it is having 0.15 nanometers in diameter and water molecule is almost 0.3 nanometers across and human hair values which is about 80,000 nanometers wide. Okay, and here bacteria range 1000 to 10,000 nanometers. Okay, based on the size and shape of the nanomaterials are classified into as follows: nanoparticles, nanocapsules, and nanofibers, nanowires and fullerences, nanotubes and nanosprints, nanobelt, quantum dots, and nanofluids. These
Yes,
are the
Usha.
based on the size and shape. The nanomaterials are classified into different types. Okay, and here the nanoparticles affects many properties such as boiling point, melting point, and band gap, optical properties, electrical properties, and they have magnetic properties also. Okay, and coming to physical properties, and these are having interatomic spacing decreases with size. And here we are taken into in the x-axis particle radius, and we are taken into in the y-axis melting point, and graph will be shown into like this. The melting point decreases dramatically as the particle size get below 5 nanometers. Okay, and here the band gap is increases with reducing the size of the nanoparticles. Okay, and here coming to chemical properties, and it has strong effect on catalytic properties. Better catalytic efficiency. The number of absorbed hydrogen atoms decreases with increasing the cluster size. And the clusters of nickel and platinum can absorb up to 8 hydrogen atoms per metal atom. And nanoparticles useful hydrogen storage on your videos, ma. On your videos. A4, D1, A6 on your videos. Okay, these are the chemical properties of nanoparticles. And coming to mechanical properties, the Young's modulus of carbon nanotubes. CNT means carbon nanotubes is 10 times stronger than steel, but its weight is 6 times lesser. 76 on your video, ma. Improved hardness and toughness of metals and alloys, ductility and superplasticity of ceramic. And superplasticity has been observed at lower temperatures and higher strain rates in nanocrystalline materials. These are the mechanical properties of nanoparticles. And coming to optical properties, when the size of the material is reduced, the scattering of light takes place due to
Sneha top.
mute yourself. Please mute yourself.
ఏం B8 ఏమకి ఫస్ట్ వీరిద్దరు గొడవ అయింది ఈ అబ్బాయి కానీ
మీకు కూడా వీడియో
చెయ్యి ఇప్పుడు అందరు చేయాలి కదా
Mute yourself, ma.
ఎవరు చేయలేదుగా
చాలా తక్కువ మంది
లీవ్ అయిపోతాను తల్లు
చాలా తక్కువ మంది ఉన్నారు.
50 దాకా
Who is that fellow? The interaction of light with the nanomaterials is with respect to particle size, hence it emits different colors. Okay, gold nanospheres of 100 nanometers appears orange in color and 50 nanometer spheres appears in green color. Okay, and bulk material of zinc oxide scatter visible light, but in nano size it does not scatter. Okay, then increased quantum efficiency of semiconductor crystals. These are the optical properties of nanoparticles. And coming to magnetic properties, when the grain size of magnetic material is reduced to the order of nanometer, the number of surface atoms increases and the magnetic domain size is reduced to nanoscale. And decrease in nanomagnetic domain increases the magnetization and increases the quality of the magnet. Okay, and sodium, potassium are the paramagnetic in bulk materials, but it exhibits into ferromagnetic materials in nanoscale. And ferrous, cobalt, nickel are ferromagnetic in bulk materials, but they are exhibits super paramagnetic in nanoscale. And nanoparticles of even nanomagnetic solids are found to be magnetic materials. These are the properties of magnetic properties of nanomaterials, and why the properties of nanoparticles are different. And it basic principles of nanomaterials can be divided into two principles, two factors cause the properties of nanomaterials to different the significant of bulk materials. They are increase in surface area to volume ratio, and the second one is quantum confinement effects. These are the two basic principles of nanomaterials. Okay, and here we are discussing about increase in surface area to volume ratio. Here nanomaterials have large surface area surface area to volume ratio when compared to bulk materials. Okay, first we are taken into the first example. We are taken into the one bulk material. Let us consider a sphere and its radius is r and its surface area is 4 pi r square and its volume is 4 by 3 pi r cube. Thus, surface area to volume ratio can be written as 4 pi r square by 4 by 3 pi r cube. Then finally we get surface area to volume ratio value is 3 by r. Okay, where surface area to volume ratio of the nanoparticles is very high compared with the larger particles. Okay, when bulk material is taken into 1 meter and when it is divided into for cubic value. Second example, surface area is 6 into half meter square. When it is divided into 8 pieces, it's a surface area to volume ratio 6 into half meter square into 8, and finally we get 12 meter square. When it is divided into 27 pieces, then we get 18 meter square. Okay, finally we observed that therefore when the given volume is divided into smaller pieces, the surface area will be increases. Hence, as particle size decreases, greater proportions of atoms found at the surface compared to those inside. Then the nanoparticles have much greater surface area to volume ratio. And coming to second one, what is second one? Quantum confinement. Quantum confinement. When the size of the when the keeping of electrons trapped in a very small area is called quantum confinement, or when the size of the particle is too small when compared to de Broglie wavelength. Already we know de Broglie wavelength. What is a de Broglie wavelength, ma? Equation of de Broglie wavelength. Anybody? De Broglie wavelength. Anybody? De Broglie wavelength expression. On your video, 67, roll number 67. Roll number 67. Ma. There is no response from your side. De Broglie wavelength expression is lambda is equal h by mv. Then the decrease in particle size increases the band gap energy, which turn decreases the wavelength of emission of radiation. The change of electronic and optical properties of a material due to change of energy levels of electrons of material in the order of nanoscale is known as quantum confinement. Here, the nanomaterial structures by rules for the quantum confinement. Okay, here the length in which the confinement takes place must be smaller than the de Broglie wavelength expression, and that quantum confinement takes place into several forms. They are quantum dots or quantum wire and quantum well and quantum bulk. What is quantum dot? It is a zero-dimensional system. Okay, the electron movement was restricted in entire 3 dimensions. It is known as quantum dots. And what is quantum wire? It is a one-dimensional system. The electron can move in one direction and restricted in 2 directions. On your videos, ma. And quantum well. It is a 2-dimensional system. The electron can move in 2 directions and restricted in 1 direction. Okay, this is known as quantum well. And quantum bulk. It is a 3-dimensional system. The electron can move in 3 directions. The electron can move in 3 directions. Okay, and these are the quantum confinement of nanoparticles. These are the two principles of nanoparticles, that are quantum confinement and surface area to volume ratio. And now preparation or production of nanomaterials. Preparation or synthesis or production of nanoparticles. Okay, and nanomaterials can be prepared in 2 ways. They are top-down fabrication and bottom-up fabrication. Okay, nanoparticles can be synthesized by 2 ways. That are, first one is bottom-up fabrication and top-down fabrication. What is bottom-up fabrication? In this method, the nanomaterials are synthesized by arranging the atoms or molecules together to form the nanomaterials. Okay, to form nanomaterials. Okay, here some of the methods are there to prepare to synthesize the nanoparticles, that are Sol-Gel method and precipitation method, combustion method. These are the bottom-up fabrication methods. And top-down fabrication method. What are top-down fabrication method? In this method, the nanomaterials are synthesized by arranging the bulk materials into nano sizes, as shown. Bulk material into nano sizes. Okay, these are the Sol-Gel method and ball milling method and physical vapor deposition and CVD. PVD means physical vapor deposition and CVD means chemical vapor deposition. Okay, now we are discussing about CVD method. What is CVD? Chemical vapor deposition method. In this method, nanoparticles are deposited from the gas phase material. It is heated to form a gas and they allowed to deposit on solid and surface by condensation under high vacuum condition. Okay, and here procedure is there to prepare the nanoparticles, to synthesize the nanoparticles. First, we are taken into the metal organic precursor is Okay, metal organic precursor is introduced into the hot zone of the reactor. Okay, and here see this diagram, all of you, and the precursor is vaporized either by resistive or inductive heating, and the carrier gas such as argon carries the hot atoms to the reaction chamber. Okay, carries to the hot atoms to the reaction chamber, and the hot atoms collide with the cold atoms and undergo condensation through nucleation and form small clusters. Okay, so all of you see this diagram, chemical vapor deposition diagram. And here CVD is the formation of a non-volatile solid film on a substrate by the reaction of vapor phase chemicals and that are called reactants that contain the required constituents, and the reactant gases are introduced into the reaction chamber and are decomposed and reacted at a heated surface to form the thin film. And here deposition can also take place due to a chemical reaction between some reactants on the substrate. In this case, reactant gases are precursors. Precursor is taken into reactant gas and pumped into a reactor or reaction chamber. Under this right condition, they undergo a reaction at the substrate. This is the total procedure. Okay, one of the products of the reaction gets deposited on the substrate. The byproducts are pumped out, and chemical vapor deposition or CVD is a generic name for a group of process that involve depositing a solid material from gaseous phase. And here micro fabrication processes widely use CVD to deposit materials in various forms, including monocrystalline, polycrystalline, and amorphous and epitaxial. These materials include, what are the materials include in CVD method are silicon, carbon fiber, and carbon nanofibers, filaments, carbon nanotubes, and silicon dioxide, and silicon germanium, tungsten, silicon carbide, silicon nitride, silicon oxynitride, and titanium nitride. CVD process is also used to produce synthetic diamonds. These materials are included in CVD method. And working concept of CVD is chemical vapor deposition result from the chemical reaction gaseous precursor is at a heated substrate to yield a fully dense deposit, and thermodynamic and kinetics drive both precursors generations and decomposition, and control of the thermodynamics and kinetics through temperature, pressure, and concentrations yields the desired deposit. Okay, and material deposition is takes place into the metal halide, is gives rise to metal plus byproduct. And ceramic deposition is metal halide and oxygen or carbon nitrogen boron source ceramics plus byproduct. Okay, where the G means gas and S means a solid material. And a basic CVD process consists of the following steps: a predefined mix of reactant gases and dilutants. Inert gases are introduced at a specified flow rate into the reaction chamber, and the gas species move to the substrate. The reactants get absorbed on the surface of the substrate. The reactants undergo chemical reactions with the substrate to form the film, and the gaseous byproducts of the reactions are disobsorbed and evacuated from the reaction chamber. During this process, chemical vapor deposition, the reactant gases not only react with the substrate material at the vapor surface, but also in gas phase in the reactor atmosphere. Then the reaction takes place at the substrate surface, are known as the heterogeneous reactions, and are selectively occurring on the heated surface of the wafer, where they create good quality films. And reactions that take place in the gas phase are known as homogeneous reaction, and homogeneous reactions form gas phase aggregates of the deposition material which adhere to the surface poorly and at the same time form low density films with lots of defects. In short, heterogeneous reactions are much more desirable than homogeneous reactions during chemical vapor deposition. Okay, here some types of CVDs are there, and that are atmospheric pressure CVD, low pressure CVD, ultra high vacuum CVD, aerosol assisted CVD, and direct liquid injection CVD, and microwave plasma assisted CVD, and plasma enhanced CVD, hot filament CVD, rapid thermal CVD. These are the types of CVD material, chemical vapor deposition. And this is a schematic diagram of CVD material. Here, different types of CVD materials are there. And here, advantages of CVD. It can be used for a wide range of metals and ceramics, and it can be used for coatings or freestanding structures, and to fabricate net or near net complex shapes. And these are used to self-cleaning, extremely high purity deposits, and it conforms homogeneously to contours of substrate surface, and it has a near theoretical as a deposited density, and CVD has controllable thickness and morphology, and it forms alloys, and it can be used as infiltrates fiber performs and foam structures, and it will be used as ports internal passages with high length to diameter ratios, and it can be used as simultaneously coat multiple components, and it can be used as powder coats. These are the advantages of CVD. And what are the applications of CVD? Chemical vapor deposition processes are used on a surprisingly wide range of industrial components. It can be used in industrial components from aircraft and land gas turbines, and chain pins for the automotive industry radiant, and grills for gas cookers, and items of chemical plant to resist various attacks by carbon, oxygen, and sulfur. Some important applications are given below. Surface modifications to prevent or promote adhesion, and these are used to photoresist adhesion for semiconductor vapors, and substrate adhesion for microarrays, DNA, and gene protein antibody tissues. These are used to these applications. MEMS coating to reduce friction, and biomems and biosensor coating the reduce drift in device performances, and it can be used as promote biocompatibility between natural and synthetic materials, copper capping, anti-corrosive coating. These are the applications of chemical vapor deposition. And the next synthesized method is physical vapor deposition. Okay, and here introduction of physical vapor deposition is fundamentally a vaporization coating technique, and it involving transfer of materials on an atomic level. It is an alternating process to electroplating. The process is similar to chemical vapor deposition, and it accept that the raw materials are precursors that equal to the material that is going to be deposited starts out in solid form, whereas in CVD, then the precursors are introduced to the reaction chamber in the gaseous state. And here working concept of PVD is, and it carried out under vacuum conditions, and the process involved into 4 steps, that are first one is evaporation, and second one is transportation, and third method is reaction, and fourth step is deposition. These four steps are involved into the PVD method. And first, evaporation. What is evaporation? During this evaporation stage, a target consisting of the material to be deposited is bombarded by a high energy source such as beam of electrons or ions, and this voltage atoms are from the surface of the target and vaporizing them. This is evaporating stage. And coming to transport stage, this process simply consisting of the movement of vaporized atoms from the target to the substrate to be coated and will generally be a straight line affair. And third stage is reaction stage. In this stage, some cases coatings will consist of metal oxides and nitrides, carbides, and other such materials are involved. And in these cases, the target will consisting of the material, consist of the metal. The atoms of metal will when react with the appropriate gas during the transport stage. And for the above example, the reactive gases may be oxygen, nitrogen, and methane are involved in this stage. And in instances where the coating consisting of the target material alone, this step would not be part of this process. And fourth stage is deposition. This is the process of coating buildup on the substrate surface. Depending on the actual process, some reactions between target materials and the reactive gases may also take place at the substrate surface simultaneously with the deposition process. Okay, and below figure shows a schematic diagram of the PVD method, and in this component, the component that is to be coated is placed in vacuum chamber, and the coating material is evaporated by intense the heat form. For example, a tungsten filament is used in this method. An alternative method is to evaporate the coating material by complexion bombardment technique, and the coating is formed by atoms of the coating material being deposited onto the surface of the component being treated. This is the schematic diagram of PVD method. And here component is there, deposit and evaporated material and vacuum and heated coating material. Okay, the vacuum evaporation of PVD process. And variants of PVD include in order of increasing novelty, evaporative deposition, in which the material deposited is heated to a high vapor pressure by electrically resistive heating in high vacuum. Electron beam physical vapor deposition, in which the material be deposited, and here sputter deposition is there, cathodic arc deposition, in which high power arc directed, and pulsed laser deposition is there. And these are the importance of PVD coatings. Okay, improved hotness and wear resistance, and reduced friction, and improved oxidation resistance. Okay, and some of the advantages are there. Materials can be deposited with properties compared to the substrate material, and these are the disadvantages of PVD method. Okay, and these are the applications of PVD. These are used in aerospace, automotive, and surgical or medical processes, and cutting tools, and dies and molds for all manner of material processing. Okay, this is physical vapor deposition. Today we are discussed about CVD and PVD methods. Okay, all of you clear this one? Okay.